All right, so just as a reminder, there is a midterm retake exam that will be for Thursday of this week. And that retake exam is effectively optional. The best score from the pre-take exam last week and the retake exam will actually be what's committed to the grade book. So if you already took the pre-take exam and you're happy with your score, then you don't have to take the retake. If you'd like to, it's not going to hurt your score. It can only increase your score. If you didn't take the pre-take, you still are can take the retake. There's no requirement that you have to take one in order to take the other. And so if you didn't take the pre-take last week, you'll just get a 0 on that one, and then you'll take the retake this week and you'll end up getting the score you get for this week. They are different exams, and so they're going to be the same length. So when I built them, I literally just sat with a Word document and I created one question, and then next to it I said, well, what's a question that's sort of from a similar area of the course that I think is similar difficulty, and then put that up there. And so I did that all the way down through it. So I think there were 37 points in the because I think there were 37 points in the pre-take, and there will be 37 points in the retake as well. So it should be very similar, but each question is totally different, but it should be of similar difficulty and go over similar content. All right, so today, originally this day on the schedule, if it wasn't during these kind of COVID times, would have been a fall break day, but fall break was canceled. But I didn't want to shake up all of the schedule, and I know a lot of students weren't aware that fall break was scheduled or was canceled, and so this here is meant to be kind of an optional lecture, so I won't be taking attendance today if that affects how you're attending. So with all of that, I just want to kind of do whatever makes sense for us to do here. So I am happy to answer questions. I'm happy to go back over the midterm review slides that I prepared before. I'm happy to go over the midterm solution set from the first midterm. And I've actually gotten over the private chat a request to do that. So before I get started, are there any other suggestions or other things that people want to make sure that we cover during this time? So there's a question, is there a lecture on Thursday? No, Thursday's lecture, or Thursday will go exactly like the midterms day was. And so the retake, I want to make sure that you have the lecture period to do the retake. And so there will be no lecture on Thursday. It'll be exactly, it's identical to the midterm, it's just a different test. Okay, any other questions before we get started? So maybe because there was a request to look at the solution sets for the first midterm, maybe I will shift my share to share those solution sets instead. So stop this share, and instead I will share the midterm solution sets. This is for midterm A, the midterm that you've already taken. At least I hope that will be what it is. It would be awkward if I shared the other one. So this here is the midterm solution set that has already been posted. That's available online. And so there was a request to go over some of these solutions. I'm not sure if it makes sense for me to just scroll down through. Was there any particular questions on this first midterm that someone would like help with?
Could you go over number 18, please?
Yeah, number 18. So let's see what that is. All right, so here's number 18 up here. Let me highlight that. I think we're focusing on this one right here. And so this one, select all the following statements that are true. So this is a question that's about linear congruential generators. And so I guess we can go through here and sort of, let's see, so you can see which ones I've marked as true. So maybe a nice exercise would be for us to look through at these ones that are apparently false and see why they are false. And so of the group that I've got here, so there's a little bit of a quorum here, why do you think A is false? So this says linear congruential generators are combined to reduce non-uniform clusters of random numbers. Does anyone have an idea of why that's false? Could I zoom in? Oh yeah, I can, if that's hard to read, let me, I can do that. We have the technology for that. Let's try, this is the easiest thing. Stop share, advanced, portion of screen. All right, so this is the question that we're focusing on down here, number 18. All right, does that look better? I hope that's rendered at a larger size. Great. Okay, so the question is, anybody know why would, so this first one, linear congruential generators are combined to reduce non-uniform clusters of random numbers. So this is false, it's a distractor. So we do combine linear congruential generators, but why do we combine them? It's apparently not for reducing non-uniform clusters. For cycle length, that's right. And so this first one here, A is false, because, and maybe I'll try to annotate on top of this, A is false because linear congruential generators are combined to increase cycle length. All right, so then the second one, a random number sequence generated by a good linear congruential generator is expected to have a large D statistic in a Kolmogorov-Smirnov test, i.e. above the critical value for the significance level. So this is sort of a combination of a question about linear congruential generators and a question about what we do with Kolmogorov-Smirnov tests with uniformity. So does anyone have a good solution or good reason why B would be false? So what, why is, what's the red flag here? What would be the reason why we would say this is clearly not the correct answer? Anybody? And I guess a hint is, does anybody remember, like I said that you should build a mental model of what these statistics are, like what a D statistic is, and what a T statistic is, and what a chi statistic is. And I said the D statistic has a particular interpretation. Does anybody remember what that interpretation was?
Well, I just remember that the D plus that we calculate needs to be smaller than the D we see from the tables.
That's right. You want the D that you calculate to be smaller. That's correct. And that's what in the chat, there was also another comment that you want it to be small. And so that is one, that should be your red flag, right there. You want it to be small. The conceptual framework here is that in the chi-squared test, the D statistic is a measure of how far you are away from a uniform distribution. So if it's a good LCG, then that means it should be fairly uniform. So if you sort of measure its uniformity, then its deviation from uniformity should be small. And you can think of D in the chi-squared test, or I'm sorry, in the KS test when applied this way, as being the deviation from uniformity. So if it's a good LCG, it should be uniform. If it's uniform, it should have a small D statistic. And then there's this question down here. Sequences from LCGs, from combined LCGs, do not ever repeat. Now, we already said that LCGs were combined to extend cycle length. And so that kind of inherently, the fact that we still say they have a cycle length suggests that they still repeat. So combined LCGs still repeat. Basically, any deterministic iterated function like a pseudo-random number generator, if it's deterministic, it has to repeat. And so you're going to keep putting numbers into it. It can't go on forever. And so it's eventually going to repeat. And so all we can do is extend how long it takes before the repeat, but we can't actually prevent it from repeating. And so that's the reason why we do clever things like combining LCGs. If there was a magic way for us to create truly non-repeating sequences, we would just do that, but there's no way to create a non-repeating sequence using a deterministic mathematical expression. So all that leaves us with are C and E. C, every sequence from an LCG will eventually repeat. Well, that's kind of exactly what I just said. Any deterministic function is going to repeat, and so any one of these LCGs is going to repeat. And then I've got here a random number generator driven by the LCG expected to have a small chi-squared statistic. And this goes back to the discussion we had up here for this D statistic. The chi-squared statistic is also a measure of deviation from the null hypothesis, where the null here is going to be the uniform distribution. And so if you have a large chi-squared statistic, then that means you're very non-uniform. It's a high deviation. So if you're good LCG, you should be fairly uniform. So if you measure the deviation from uniformity, it should be low. And the chi-squared statistic is one measure of deviation from the null. And so it should also be low. And so that's why C and D are both the true answers there. Anybody have questions about that explanation?
Yeah, sorry, could you just explain why letter A is like false? And like, so what would the equivalent like true statement be?
The true statement there would be that LCGs are combined to increase cycle length of a linear congruential generator. So an LCG already has the ability to generate non-uniform groups of numbers. And so we don't combine them to, so it's not like you take an LCG that has a clustered group of numbers, another LCG that has another clustered group of numbers, and combine them and you get them more uniform. You need to start out with uniformity. So you have one LCG already is uniform, the other LCG is already uniform, but this LCG has only got like 1,000 number cycle length, and this other LCG only has a 1,500 number cycle length. If you combine them, then it's possible to get a cycle length, say, that is the product of their two cycle lengths. So the combination is not for uniformity. It's kind of for independence, really. You combine them to produce an even longer string of independent numbers.
Okay, that makes sense. So wouldn't, so if it had said LCGs are used to reduce or used to like create non-uniform clusters of random numbers, would that be a true statement?
You could say that, I mean, a true statement, it says with the proper choice of parameters, an LCG can produce effectively uniform pseudo-random numbers. That would be that would be a reasonable true statement.
Okay, that makes sense. Thank you.
Mm-hmm. Okay, so any other questions about the midterm solution set? Could I go over question 9 and why fraction? Yeah, okay, I had a feeling that this would be one, so I'm glad you brought that up. So question 9, so we'll zoom in over there. Let me clear these annotations. 7, 8, oh, right, so it's not 9 on this one. Let me see, it would probably be, because I've typeset it, so all of these were one question on the Canvas test, and so I have to find it, which fraction of the test period, maybe I should search. Yes, question, what is 13 on the paper-based version. Sorry that the numbers don't match up. I wrote the paper-based version first and then converted it into a Canvas version. And then so the numbering doesn't necessarily work because I could put all these into a match. Anyway, so this is the one I think that is being referred to here. And so select all of the descriptions that are most likely to describe delays as opposed to activities in a simulation model of test taking. And my claim was the only one that is a delay would be the time a student waits to receive help from a proctor while the proctor is helping another student. And so I think there were a couple of students who had a question, said, well, why isn't this one a delay? And so you have to remember that delays and activities are in units of time. This D is actually a utilization. It's the total test period, so that's the total time, and it's what fraction of that, say 20%, was the instructor or was the proctor busy helping students. And so this, I guess I'll scribble that in. This was a utilization, not a delay. A delay would be something that would actually be expressed in units of time, like, I actually waited 5 minutes. But this is a measure of how busy the resource is. And so that's why it's not a delay. On the other hand, you can also look at it and say that it's also in some ways a measure of how much time the proctor was busy doing things and not waiting. Maybe that's another reason why we don't view it as a delay. The other thing I want to stress, and I think this is kind of an important thing, is that adding together activity times does not give it a delay. So not any, like I can't just say that, okay, well, the instructor, I'm going to grab 5 random students and I'm going to see how long the instructor spent with those 5 random students and add that together, and then that will represent a delay. But so a delay has to be a contiguous block of time. So it has to be that one student had to wait for an instructor to get through 4 particular students. And so those 4 particular sequential activity times add together for the delay that the 5th student felt. So there's a question, but the utilization can help us calculate the delay time. You might, that's hard to say. A utilization can tell me how much time was spent actively doing value-added work, but it is difficult for me to tell with a utilization number how much delay was being generated for other entities. And so it might be that if you get a burst of traffic, you know, 10 people raise their hand at once, and then the proctor has to go and help those 10 people. And so it helps the first one immediately. That person says no delay. The second person had to wait for the first person, so they had to delay, and all the way down through there. But he can finish all 10 people, say in the first, I don't know, 10 minutes of the period. And it might be that in the rest of the period, nobody else raises their hand. So in that case, the proctor's utilization might be, you know, 10% or something, but it doesn't really tell us the difference between the proctor spending that 10% in a spread out way, which wouldn't generate any delays, or spending it all at once, which would generate delays. So utilization really is decoupled from these delay metrics. It's really about how strained the resource is. So if you see, it is true that if you see a lot of delay, that probably tells you that it would benefit you to have 2 proctors, you know, an additional resource, more resource capacity. But then when you go to your boss or whatever, so like when I say I am really busy proctoring 475, and I go to my program chair and I say, can you give me another proctor for the exam? The program chair might say, how busy are you? And I say, well, you know, I spend 10 minutes out of every 75 minutes, but during those 10 minutes, I can only, like, students have to wait the whole entire time. And she might come back to me and say, well, you know, 10 minutes out of 75 minutes, I can't really justify, you know, tying someone else up for 75 minutes. Your students are just going to have to wait. So they interact, but they aren't like linearly related. So does that help? Are there any more questions over that? The D, it was meant to be utilization, and that fraction was supposed to key off that it was, you know, you're dividing a time by another time, a time by a total time. All right, any other questions then about the midterm solution set?
Sorry, could you go over 15 really quick?
15 on the paper-based form. So you mean this one here, or 15, or a different one than this 15?
Yeah, just these a couple of questions just about like the how to tell if the PRNG is like good or not.
Okay, yeah, I can do those real quick, and then I also have got a question here. There's question 29. So this pseudo-random number generator. So we look at this, and so this first one here, you know, when you're looking for, does this look like there's any signs of deviation from independence, and are any signs from deviation from uniformity? It's only 10 numbers, so it's a little hard to see, but I tried to make things as clear as possible that 10 numbers would show. So I tried to make the effects really strong. So in this one, I look through here, and I see that I've got high numbers and low numbers that are kind of mixed in together. There doesn't seem to be any predictable pattern. So it's true that this one's high and this one's low, and this one's high and this one's low. And so, you know, that it looks like there might be a little bit of a zigzag there. And that, now that I see that, well, that's maybe a little bit of a pattern, that I know that if I get a high number, then I'm going to get a number lower than it later. But it's not clear exactly what I mean by high and low. So it really seems like these numbers, there's not a real good way to predict what number is coming next based on that number. So it seems to tick the independence box. So that seems fine. And then when I look through here, I see that if I were to bin these, you know, kind of do a chi-squared test, not a legal chi-squared test, but kind of a pseudo chi-squared test, or imagine in your head if you were kind of doing a pseudo KS test, then I can kind of see that there's representation from all over the number line. So if I have 10 numbers, then I'm saying that I should see about one number from 0 to 0.1, about one number from 0.1 to 0.2, about one number from 0.2 to 0.3, and so on. If I go through here, I see, well, there's my one number from 0 to 0.1. There's 0.1 to 0.2. Then I've got, this is maybe 0.2 to this is 0.2 to 0.3, 0.3 to 0.4, 0.4 to 0.5, 0.5 to 0.6, 0.6 to 0.7, 0.7 to 8, 8 to 9, and 9 to 1. And so these are clearly distributed uniformly across from 0 to 1. So seems to also be uniform. So yeah, that seems good to me. That seems like a very reasonable sequence. Now, if I contrast that, I can scroll down a little bit to this next one. So clear these annotations. And in this one here, then if I look here, then I see that there's really two clusters of numbers that were generated. There's numbers that are around 0.85 or so. So that's these ones that I've kind of put a line above here. So notice there's like 0.89, 0.83, 0.93, 0.93, 0.95. All of those occur on kind of the right-hand side of the number line from 0 to 1. And then there's numbers that seem to cluster around, I don't know, 0.3 or so. And so 0.25, 0.3, 0.26, 0.32, 0.33. And so those are all kind of clustered over there. So I don't get any numbers that are really low. I don't get any numbers that are in the middle. So it seems to violate uniformity. They're not everywhere. Now I look at it and I can't really predict a pattern that's going on there. That just seems, so I can't really say that it's not independent, but it's clearly non-uniform. And then I can contrast those with this group here. Clear the annotations. And so here, these numbers are sorted. So whenever you see sorted numbers, then you know it's not independent because they're just monotonically increasing. And so now I know that if I get a number, the next number is going to be higher than it. And that's a clear pattern. So they, you know, they're not independent. And then because they're sorted, it makes it even easier to see the clustering that I talked about up here. So these are actually the exact same numbers from the previous question, but I've just sorted them. And so we've got the same non-uniformity. And again, now it's even clearer now that I've sorted them out. So I've got a cluster that are down here around whatever 0.3 and a cluster that here around 0.93. So they're not uniform as well. So they violate kind of both tests. So those are those three questions. So does that make sense? Are there further questions on that one before I move on to the next one? All right, so I'm gonna go to question 29 and then there's a query for question 27 from the online version. While I scroll down to 29, can you paste in some text from 27 so that I can, you know, to sync that up with the document that's in front of me, just so I can search for it, or just a couple of keywords so that I can find it. And then I will go to 29 first. So assuming that we mean this 29 here. So just to confirm, this is the 29, good, great. All right, so this is a little question about ARENA and also just kind of, I guess, empirical CDFs. Which of the following ARENA expressions correctly encodes an empirical CDF for a 5-sample data set? And so what we have to, so the ARENA syntax is down here. And so the syntax for the discrete random variable with its own CDF takes the form of an inverse CDF. And so you take every outcome, which is the even numbered arguments, and you pair them with their cumulative probability, and those are the odd numbered arguments. And so that tells me that the odd numbered arguments of the disk should be monotonically increasing from 0 to 1. So if I look at the odd numbered arguments of this line of B, then I can see that 0.1, well, that's maybe reasonable. 0.55, that increased, that's great. 0.95, that looks good. But then it goes above 1. So 1.85 and 2, these both go above 1. So that tells me that it's not valid syntax. It's not properly encoding an inverse CDF, because the odd number arguments, the arguments at position 1, position 3, position 5, those are ones that are not going from 0 to 1 in a monotonic way. Similarly, so it's not B. Similarly in C, then I look at this and I see the odd numbered arguments are all 0.2. And so this kind of tells me that it's trying to encode something like a probability mass function, but it's supposed to be an inverse CDF, a cumulative distribution function. So the odd numbered arguments are supposed to constantly be increasing from 0 to 1. So the fact that these odd numbered arguments are all 0.2 tells me that this is not correct as well. So then down here in this fourth one here, I see that I've got the same problem that the odd arguments are. So I've got 0.1, 0.55, 0.95, 1.85, 2. And so again, I've got this same problem that the odd arguments are not monotonically increasing from 0 to 1. So that has also got to be incorrect. And so I've got none of these options, but if I look back at the top here, I can see, does this one make sense? Well, I look in the odd numbered arguments. So here, 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 and here, those are monotonically increasing from 0 to 1. That's good. But now I need to say, but this is for an empirical CDF for a 5-sample data set. Well, if I remember, an empirical CDF basically associates each sample with its rank in their kind of ordering divided by the total number of samples. And so the first sample is going to be 1 over 5. The second sample is 2 over 5, and so on. And that's what we see here. 0.2 is 1 over 5. 0.4 is 2 over 5. 0.6 is 3 over 5. 0.8 is 4 over 5. 1.0 is 5 over 5. And then in the second arguments here, I've got the sorted data. So these are all moving in the right direction, and they are clearly data. So that's why this kind of meets all of my conditions there. So it definitely looks like it's encoding a true empirical CDF, and it's doing it in a proper syntax for ARENA. So any other questions about that one? Great, all right. And then there was a question then about question 27. So let me clear annotations here. And a random probability density function. Oh, that's not how to spell probability. All right, so I believe this is the one. Is this the correct question that was asked about? I just want to make great. Okay, so in this one, let me scroll a little bit. Or try to scroll. Oh, I can't scroll because I'm at the bottom of the page. So let me move this a little bit. All right, so what do we got here? We have a probability density function, and I asked you to calculate a CDF for this probability density function. So you've got to do the piecewise integration. And I'm asking you, after you've calculated it by yourself, so you don't like have a play to enter it, then to evaluate your CDF specifically at the value of 10. So that's what I'm asking here. F of x is equal to 10 right there. So this, and pardon my mouse is a little jumpy. I think I have some Bluetooth issues with the mouse that I'm running. So this normally would require you to piecewise integrate this whole thing, but I've tried to engineer this so that you can kind of use your geometry to sort of figure things out. Or even if you do the kind of all the math, then you can then it should be not a whole lot of work you can do. So the fact that I'm asking for x equals 10, I know that that's in between these two pieces, this 0.2 piece and this 0.3 piece. So that basically means that f of x, so the CDF evaluated at 10 is just going to be all of the area underneath these three pieces. So the 0 piece, which is going to be nothing, the 1 piece, and the 2 piece. And so down here, I've got this, that's what I've encoded here, that I'm just taking the area underneath all outcomes that are less than 10, which is just going to be the integral of this first piece from 0 to 2, so that'll be the 0.1 component. And then it'll be the integral of this second piece, 0.2, and that's this 0.2 component. This one goes from 0 to 2, and this one goes from 2 to 3. So if I take the integral of a constant, so the 0.1, the integral, the antiderivative of 0.1 is just 0.1 times x. And I then have to evaluate that for the limits of integration from 0 to 2. And so that's all that I'm doing here. There's the 2 and there's the 0. And then the integral of 0.2, the antiderivative of 0.2 is 0.2x, and then I can evaluate that from 2 to 3, 2 to 3. And then that's where I get here, 0.2 times, and then there's my 3, and there's my 2. And so then I do the math, and I end up getting 0.4, and 0.4 is between 0.35 and 0.5. And so that's one way to do it. The other way to do it is if you were to plot the probability density function here, then you would kind of see that you get a rectangle with a height of 0.1. So this region here is going to be a rectangle with height of 0.1 and a width of 2. And this one here is going to be a rectangle with height of 0.2 and width of 1. And so that's all you're adding up here is these two rectangle areas down here. Does that answer the questions on that one? Is it clear where that comes from? Great. All right, and then I've got a question. Let me make sure I didn't miss any questions. Got the 29, got the 27, and so now I've got a question over 24 version A. So I'll clear this. Thank you for all of these questions. It's always, it's great when you guys participate like this. And if I can get this to scroll, oh, it's because I'm searching. All right. There we go. So this was 24 version A. All right, can you paste in some text from 24? This is a thing, again, where the numbering doesn't line up, and I don't have the Canvas one in front of me. I only have the paper-based solution set. So which one was 24? I see 8 numbers from a new and untested are shown below. They have been sorted in increasing order. Okay, the increasing order. All right, I think then that's this one. Is that correct? Okay, great. And so this one here was a question where I wanted you to apply a Kolmogorov-Smirnov test and to basically calculate the statistic here. And so I've already sorted the numbers for you. And so all I've done in the solution set here is then I've then marked the kind of expected intervals where each one of these numbers would fall into if it was uniformly spaced. And so there are 8 numbers. And so 1/8 is kind of my increment that I jump in each one of these bins. So this is 0 to 1/8. This is 1/8 to 2/8. This is 2/8 to 3/8, 3/8 to 4/8, and so on. And so I then am going to calculate the maximum difference from the data, which is in the middle, and its 2 boundaries. And so here I'm seeing that between here and here, the 0.125 minus 0 gives me a 0.125. 0.25 minus 0 gives me a 0.25, and then the 0 minus 0.125 gives me a negative number, but I don't worry about the negatives. And so I take the max difference here as 0.25. So I do that all the way up here. I'm just going to take the difference between, and let's see if I can annotate. I'm taking the difference between the top and the data, and then the difference between the data and the bottom. And then of those two, I'm taking the maximum of those, and then putting that into this max diffs line down here. And then out of all of those differences, I then take the maximum one of those. So this is like the max diff. And if I look back through these, then that is the 0.5. And so that will end up being the D statistic that I end up answering with here. Does that make sense? Are there any questions over that? Is it clear where I got the line of numbers down here? Great. All right, there was a question 28. It looks like there's 2 for question 28, so that's exciting. Can you go over 28? A random variable is the inverse CDF. So let's search for that. Okay, inverse CDF, that's down here. Let me clear this stuff. And looks like this one. Just want to make sure that, does that look right to everybody? I'll assume yes. All right, so with this one, we have, I've given you the inverse cumulative distribution function. So, and the question then is, what is the range of this random variable? And so if I were to draw out the CDF here, then I would have X over here and I would have F of X here. And this CDF would, let's say the CDF was, it's got to be shaped like a particular thing. And so if it was shaped, for example, like this, then as it would be for an exponential random variable, then I know that it's on the y-axis, it would go from 0 to 1. And if I were to then if I were to invert this, that's sort of asking for, all right, where does it go on the x-axis? And so, in other words, if I were to plug in any number, if I could plug in the full range of 0 to 1 through the y-axis, then where would it map down to on the x-axis? And so for an exponential random variable, if you plug in 0 to 1 on the y-axis and push it through here on the x-axis, you get a number from 0 to infinity. And so I've given you the, and that's just an example, so maybe I should clear that, just leave it up there for a second and then clear it because that's not this one here. So here I've given you the inverse CDF. And so I've actually given you the ability to plug in all numbers from 0 to 1 and then see what they map out to. So the real question is, if I were to plug in numbers of R that were between 0 and 1, then where would the inverse come out as? Well, I know that if I take the square root of all numbers between 0 and 1, then the square root is also going to be between 0 and 1. I know if I then multiply that square root by -4, then the resulting numbers are going to be between -4 and 0. And so that's where I end up getting this between -4 and 0, and that's where I got that answer right there. Nope, sorry about that. Does that make sense? Okay. And so there was a question. So we just plug in 0 and 1 to get the answer. Most of the times that's going to be, there can be some funny things that happen with that R value. There could be a 1 minus, there could be a piecewise thing. But the question is, you sort of have to ask yourself, if I were to sweep R from 0 to 1, then I need to sort of be able to reason through where the range of that inverse transfer, that inverse CDF is going to sweep through as well. So for this particular one, I think, yeah, that's a great strategy. You plug in 0 and you say it comes out to be 0. I plug in 1, it comes out to be -4. And I have no reason to believe that anything funny is going to happen in between there. So between 0 and 1, it's probably going to sweep smoothly from -4 to 0. That is, I think, a good strategy for this one. But if I were to give you something a little more complicated, maybe something that was piecewise, then you might need to be a little more clever. But the fundamental idea is you say, if I were to plug in numbers between 0 and 1 and sweep through all of them, then what would be the resulting sweep on the output of that inverse CDF? All right, so are there any additional questions? And just to double question, when we say range, we mean the values of the, so the, when I say range, with respect to a random variable, I'm referring to this Rx that we defined. And that is the numerical range of outcomes. And so I don't want to refer to it as just something on an x-axis or a y-axis, but it's specifically the outcomes that we might get in the numerical version of this random variable. So if I've got a coin, it could come up heads or tails. But in order for me to turn that into a probability distribution, I have to assign heads to something. I'll call it 0, and maybe I'll assign tails to 1. So the range of the random variable that models the coin is going to be discretely 0 and 1. But I could have chosen 4 and 5, and so then it would be 4 and 5. So the range of the random variable are the numerical values that all of the outcomes from the experiments map onto, if that makes sense. And so for an inverse CDF, the range of the random variable is kind of the y-axis of the inverse CDF. For a CDF, the range of the random variable is the portions of the x-axis that correspond to a non-constant CDF. So if your CDF is like, it's got steps where it's like it ramps a little bit and then it's got another, you know, and so each one of these constant portions do not contribute to the range. Only the kind of rising portions contribute to the range. And so for this random variable, the range would include here and here and here. And so if this was a CDF, then it would be the numbers that are down here, and down here, assuming this is a CDF. If that makes sense. That's a little ugly. Any other questions about that one? All right, and while you're thinking of questions, I just wanted to speak a little bit about the final exam because it is a funny week because we've got the cannibalized normal finals week for innovation quarter that forced us all to put our finals during the last week of classes. So that's not too bad for this week of that for this class because the Tuesday of that week was just going to be a final exam review and the Thursday was originally going to be a pre-take and then you'd take the retake during finals week. Because I can't give you the retake during finals week, then I'm going to do something a little different. And I've never done this before, but people have experimented with this. I'm going to do what's known as a 2-stage final exam. So that means that on Thursday, I'm going to give you something that would be equivalent to that pre-take. It'll be a final exam designed for a class period. You have to take it with lockdown browser. You're going to get a fixed amount of time, 90 minutes. And you'll have to take it sometime during that day, exactly like the midterm for that Thursday. But it will only contribute to 80% of your final exam score. The other 20%, I'm basically then going to release on Friday of that week. I am going to release the exact same test. And that test you will not have to use lockdown browser for that test. And I will give you 24 hours to take the exact same test again, and you can collaborate. You can talk to your friends in the class, you can look at your notes. It would be a totally collaborative way to take that final exam. So your first go is independent. It's got to be independent in lockdown browser with only formula sheets, no collaboration, exactly like the midterm. And then whatever score you get will contribute to 80% of your final exam score. And then the other 20% is the exact same test, but you can then collaborate with each other. You can say, I really had a difficult time with number 14. Can you, did you have a good, you can sort of, help each other, or you can go back and look at your notes and say, number 14, I can't really figure out that one. So, what went on there? And then you can re-answer that. So you're not totally, it's not correcting your original exam. You still get credit for your original exam, but that other 20% of your final exam is going to be the ones that effectively is sort of open book and even open students. So, and it's going to be during that Friday. So it's immediately the day after for that whole 24-hour period. That's my plan. So I've never done this before. If you have concerns about that, then please let me know. Send me an email so that I can consider how to, how to change that. But right now, I think that's what I'm planning on doing. If someone brings up a problem that they could potentially come up with that, then I might have to rethink that. But that's what I'm hoping to, unless someone comes up with a particular issue they have with that structure. And on the Friday exam, we say what platforms? Oh, you can only collaborate with, so in some ways it's a little bit of an honor system here, but you can only collaborate with other students in the current class. So I don't want you going to Chegg and asking questions there or any of these other sites like that. You can use the notes for the class that you've taken. You can use the notes that I posted on Canvas. You can use the textbooks, and you can chat with each other. Ideally, that's all that you have done. What I haven't decided yet is whether the Friday exam will be a group exam. So there's a downside of it being a group exam that you have to form groups ahead of time, and and then you're kind of like, well, how do you choose? And maybe you had a hard time finding it. So it'll probably be an individual exam, but I'm really still. I'm hoping that you'll kind of be checks on each other and that you'll take that honor pledge seriously, that I don't want you collaborating with folks outside the class. I want you only using the class's materials and the other students in the class. I don't want you reaching out to anything outside the class. And the final exam is going to be cumulative, but it'll be heavily weighted towards the stuff after the midterm, because the stuff after the midterm uses all the stuff before the midterm. So it's technically cumulative, but certainly highly biased for the stuff after the midterm. All right, so any other, and I will make that those announcements again to the whole class, because I know there's only a limited set of people who showed up here. This is video recorded, so hopefully other people review it, but I'll remind you of that. I may forget to update my slides to put all that in it, because I'll have to undo those updates because I probably won't do a two-stage in future semesters. But for this semester, we've got this special deal where I'm going to try this two-stage thing out and see how it works. Yeah, thanks for the feedback. Great. Okay, I'm glad I'm seeing the positive feedback already. But again, if you have negative feedback or positive feedback you just don't want to share in the chat, then feel free to send me that or give it some thought. Any other questions that you might have? We still have plenty of time left if there's anything else you want me to go over, anything you're not feeling comfortable with. Lots of resources online as well that I'm happy to discuss, Canvas resources, the previous midterms, if there's questions about those, anything else. All right. So I forgot to look to see what of these questions seemed to be the hardest for everybody based on the statistics. But what I seem to remember when I flipped through all of it is that I couldn't actually find one question that was knocking everybody out, and that was kind of weird to me. I noticed that there were several students a small handful that got a 36 out of 37. Usually when that happens, when I see no perfect scores, then that often means that I've made a mistake. And so I go and if they all miss the same thing, then I go and I say, oh, did I accidentally put the wrong answer? And I think all of the, whatever was 3 or 4 students who got a 36 out of 37 actually missed different answers or different questions. So it really was a very uniform distribution of performance. So I can't say that like this one was is much harder than this one. Even little things like that utility one, a couple of people emailed me and they said, well, shouldn't the fraction also be a delay? And so I went back and I said, well, did I make that one too difficult? Was that sort of impossible? And then a wide range of people got that one right too. So I couldn't from what I remember, without going into a detailed analysis, I didn't see any one question from the midterm that was uniformly like, or that everybody just had a problem with. So, so that's why if you've got another one that you personally would like to, I'm sure someone else out there would be interested in it as well. And likewise, I wouldn't say that there was one question that everybody except one person got, right. So there was no questions that were like super easy, but also there apparently were no questions that were generally hard. So there were just questions that hit individuals differently. So anything else? I guess I will scroll through here and just scan through. Everybody seemed to get this inverse one. We've had no questions here about this one, so I assume that this one was okay and the signage made sense here. So that's good. I saw really good performance on these. So I was, people seem to kind of know their distributions pretty well. Keep in mind that on the next version, if there is a question like this one, I may sample, so to speak, from distributions other than these. And so make sure you study not just these, but the full range that I kind of told you to, that, from the discrete and the continuous side. I kind of gave you like 10 of them that I said you should kind of feel comfortable with. I didn't notice many problems with the discrete event system simulation problem, which was, I thought was a good sign. Yeah. People seem to be pretty comfortable assigning these things, so that's good.
Sorry, could you go through for the different distributions where you have to choose the distribution that you were just at before?
Yeah, so do you want that question?
Yeah, so like the difference between the exponential and the Erlang.
So this is that problem there. And yeah. Okay. And so you just wanted me to go over each one of these? Oh, I think my internet connection is a little flaky.
Like the Erlang and the exponential.
Okay. Oh, yes. All right. So, so an Erlang distribution, does anybody remember basically what an Erlang distribution is meant to model? Like it's something very special. Anybody have a quick conceptual model? Yeah, it's a sum of exponential random variables. So we refer to like, we often say an Erlang 6 distribution, and that would mean it is the distribution of when you add in 7 exponential random variables. And so Erlang distributions are often used in queuing systems. If you want to sort of say that a resource is going to be busy continuously for, say, 10 customers. And so you would like to say that, okay, well then how long is it going to take that resource to free up? And so you could then say, well, what's the distribution of time it would take to get through 10 customers, given that each customer's service time is exponentially distributed. And so that would be an example of something you would use an Erlang for. Or you could ask, how long are we going to have to stay open? Yeah, right. So there's a question to this. So this one here, D, this would be considered an Erlang 5. That's an excellent point. Yeah. And so the other thing I would model for this is the time required. And this is exactly this. So if in queuing systems, you could say, how long is it going to be? Like we're going to say every day we're open so long that we can serve 10 customers. It's a weird thing, but we're going to close down after 10 customers. And so you could say, well, then how long are you going to be open each day? Well, an Erlang 10 would end up modeling how long you're going to be open each day, assuming each customer arrives independently. Because if the customers arrive independently, their inter-arrival times are exponentially distributed. And so then the sum of all those inter-arrival times till you accumulate 10 customers will be Erlang 10 distributed. In this case, Erlang 5 distributed. So that's that Erlang distribution. And I forget what the other one we asked about was Erlang, and then what was the other one you wanted me to highlight?
It was just the exponential one, but I think it was just because I mixed the two of them up, and that's why I was confused. But I understand now.
Excellent, great. Yeah. So our exponential is our kind of go-to for I have a non-negative waiting time and I only know the mean. So I'll go for the exponential. And by best choice, that is, we often use maximum entropy is a kind of a fancy metric for deciding best choice. And so this just happens to be the maximum entropy distribution when it's non-negative and have a known mean. So any other questions that have come up here? There was a comment about reliability. In case I ask, the Weibull distribution is kind of the go-to distribution for reliability engineers. So the Weibull distribution is, if you want to model generic failure times, so you have a failure time that has, a failure time with memorylessness is an exponential. So that would be that knowing how long the light bulb has operated doesn't give me any information on how much longer I have to wait before the light bulb would fail. And so that's what we mean by a memorylessness or a memoryless failure distribution. But if you did have some memory into it, so if you know that, man, that light bulb has been on for 10 hours, it is definitely going to fail within the next 2 hours, then that suggests that you can use a Weibull distribution. And the Weibull distribution is kind of a way to stretch the exponential distribution out to sort of get rid of some of the memory so you can get failures that cluster late or cluster early. So it's kind of a programmable exponential where you can tune you know, where things cluster or if they don't cluster. So if you hear reliability, think Weibull first. And then if somebody says constant failure rate, that constant is basically is another way to say memoryless. And so a constant failure rate is an exponential, but a generic failure distribution, Weibull is an excellent choice for that. All right, any other questions? All right, so there's 15 minutes left in regulation. And I'm happy to take suggestions for how to use that 15 minutes. There's a question, can you have a memoryless Erlang distribution? That is an interesting question. So if there is a, there's someone in the room here, do you have an answer for that? So like, we have Erlang distributions and we usually refer to them as Erlang 1, Erlang 2, Erlang 3. So if there is an Erlang distribution that has memorylessness, which one would it be? Does anybody have a guess for that? It's kind of a degenerate Erlang distribution. Erlang 1, that's right. So the Erlang 1 distribution, and I guess I can type this in the chat, Erlang 1 is a synonym for exponential. And I guess I could also put that in this little note here, if it will let me click on that note. Oh, I see, I have to get rid of my annotations. So the Erlang 1 is a synonym for an exponential. And likewise, a Weibull with shape parameter k=1 is a synonym for exponential. And so the exponential is the only continuous distribution with memorylessness, and the geometric is the only discrete distribution with memorylessness. And the geometric is basically a discrete version for exponential. All right, any other questions? That's an excellent question. I could definitely see myself putting something like that on a test, is you know, something about getting you to put down that you understand that an Erlang 1 is just an exponential. So what we'll find after the midterm when we start input modeling is that ARENA likes to favor, this is the Excel expression one, will favor Erlang and Weibull distributions when it should be picking out exponentials, and that's because the Erlang and Weibull are flexible and they also can match exponentials, and so but they can also match slight deviations from them. So that's like a trick that definitely will be very important come final exam to be able to tease out the difference between Erlang, Weibull, and exponential, because Arena tends to want to use the flexible ones when it fits data for you. So there's a question about question 20. It's the Excel expression. So let me just search for Excel. So this, I believe, is this one. Is this the correct one that you're talking about here? Great. Yeah, so, so this one, I've kind of put the solution over here. The idea here is because we're looking for, we need to realize samples. And so your trigger there is to say, if I've been given a CDF, the way I realize samples is I need to use the inverse transform technique. So I need to invert the CDF to get a formula that I can plug into Excel to sample from this distribution. So I look at this distribution, or this formula here for the CDF, and in order for me to invert it, I look for the regions of the CDF that are non-constant. And so that means it's this middle region here is the only region that's non-constant. So I am going to then set my R equal to 1 minus x squared and then solve for x. And so that's what I do here. X squared is equal to 1 minus R. That allows me to take a square root, but since there's a square root, I've got to make a plus or minus decision. So for this range, and it's the whole range, but for this range, then I see that I want this, when I plug in R values, so when the R value goes from 0 to 1, when I plug them into the formula, I want the formula to spit out values that go from -1 to 0. And so if I look at this square root here, if I plug in 0 to 1 inside here, if I chose the plus, then I'm going to get positive x values, and I don't want that. And so that's why I end up choosing the negative. And so that's the correct expression down there. So now I just need to implement this in Excel. And I know that some of you might not be that familiar with Excel, but I was hoping that you could kind of work through this and kind of parse these words. And so I'm looking for a negative square root of 1 minus R, where R, we know in Excel, is implemented by rand. And so that's why I got this. This is just -1 times the square root of 1 minus R. Now, if I was really being tricky, then I could have gotten rid of the 1 minus R and just replaced it with a rand. And so if you read the textbook about the inverse CDF, then they mention that a common optimization is that whenever you get 1 minus R's in inverse transforms, you just replace them with R's. Because if R is uniformly distributed, so is 1 minus R. So if so seeing a 1 minus R is equivalent to just seeing I need a uniformly distributed random number there, so I might as well just make it an R, and that way I get rid of one subtraction. Because if you're drawing a million numbers, then getting rid of one subtraction every time you draw one of those numbers can actually speed things up. So that'd be an optimization that's kind of more advanced. That's more final exam territory. But at least for the midterm here, I just left it in the 1 minus R, so to try to make it exactly like this formula. So are there any other questions about that one? Is it pretty clear how to handle that? Great. All right, so we have about 9 minutes left. Is there anything else burning a hole in your question pocket? As everybody was, are you comfortable with this crazy discrete one? I know that sometimes people have issues with the discrete inverse transform method, and so these can be sometimes challenging. Did anyone have questions over this one, or did this one make sense? And I guess I'll just go and chat here. I just highlight this one because these discrete inverse transforms have in the past been difficult. I've noticed that more recently they're not as difficult. So perhaps I'm highlighting them more ahead of time, and so students are more prepared, or perhaps it's the number of samples from the midterms. But in case you had trouble with this one, the key to this one was to convert the probability mass function here into a probability cumulative density or cumulative distribution function. And so the 0.5 or 0.25 is carries over. Then you add the 0.1 to it. That's how you get the 0.35. Then you add the 0.65 to it, and you get the 1. And then these become kind of fence posts, so that if I were to draw a random number like these random numbers between 0 and 1, then if you get a number between 0 and 0.25, that first number, then you should map it to this outcome, 1. And if you get a number between 0.25 and 0.35, you should map it to 2. And if you get a number between 0.35 and 1, you should map it to 3. So I'm just saying basically anything before 0.25 gets mapped to 1, anything between these two gets mapped to 2, anything between these two gets mapped to 3. And so if I read across here, I can see that 0.381 shows up in this third group. So it maps to the third outcome, which corresponds to the large coffee cup size in the outcome space. This one here, 0.002, that is in this first range. So that maps to 1, which is the small coffee cup size. And then this one, 0.683, that also is in the larger group, which maps to 3, which is the large coffee cup size. So these 3 numbers here correspond to these three outcomes here. So hopefully that makes sense. Any other questions? You might review this 31 was a one about drawing your own random numbers, and unfortunately, as I mentioned in the note over here on the side, I made a typo in the in this formula up here in the Canvas-based version of it, which meant that after a couple of students did their exams and I noticed that there was a problem that was evolving for this one, I had to go in and give everyone credit for it because I screwed up this one, and I could have fixed it, but then that would be unfair to the ones who solved it. I'm not giving free credit on any one particular one unless a problem crops up again on the next midterm. So I would make sure that you feel comfortable with this solution here. And so notice the trick here is I gave you the seed, a seed of 3. So that indicates that this is the seed. And then I say, what is the next random number? Well, because I've indicated the seed, and then you can tell that this is the multiplier here, and this is that increment over here, this is the modulus here. And if you go through that math, then it should agree that 0.72 is the correct number. So that tells you that in the next line, you're going to take out the seed and put 72 in there instead. And then you can then go through there and you find out you get 87, and then 87 divided by 100 gives you the 0.87, which is where you got that answer down here. So that was what was intended for you to do, but because I ended up putting a 30 there instead of a 35, just in my fat fingers typing through there, then none of the answers that I gave matched up. And so I ended up having to fix that. But make sure that you're comfortable with this one moving into Thursday's midterm, because you may be asked to do something similar to that. Because again, I try to make the midterms match as much as possible when I design the questions. Any other questions? We have about 4 minutes left in regulation time here. And this video will be posted just like the normal, but no attendance today. Just an optional lecture for help. And I'm just going to scroll through here to see if anything else pops up here. So know how to read your statistical tables. Apparently no questions on that one, so that's good. Delays versus activities. A good exercise would be to go through this one and pretend like I said activities here instead of delays and see which ones you would pick. So, you know, that's a nice one to do too, because like, so, you know, if I'd say like, well, instant, that's an event, that's not an activity or a delay. Time between two students arriving, well, the time, our inter-arrival times are activities because we kind of know their distribution ahead of time. So C would be an activity. The fraction test period, that's utilization. Time needed for proctor to help an individual student, that's a service time. And so that would be an activity. So I would say that C and E would be two activities here. So, and so that would be a very reasonable question, you know, to flip those two things around. Seed questions, these activity event delay questions, and then that's pretty much it there. Model definition sort of questions. All right. Any other questions? All right, looks like things have kind of dried up and we've gone through most of the really tough questions, I think, on the midterm. If anything else comes up, please feel free to send me a note or post something in the discussions or on the Slack channel. I'll take a look at those. Again, no lecture Thursday. Thursday is set up exactly like the midterm was before. Basically, Thursday morning at midnight, Arizona time, the midterm becomes available, and then you get 24 hours Arizona time to take it. When you start taking it, you'll get 90 minutes from your start. You'll have to use Respondus Lockdown Browser. You answer it, you hit submit, and then Friday morning, then the solution set will become available. I think you'll know your scores immediately, but then starting Friday morning, you should also be able to review your individual progress. So you'll know your total score, I think, immediately, but then you should be able to go through and without Lockdown Browser Friday, see how well you did. And then we'll just take the, and it automatically in the grade book, we'll take the maximum of those two scores and apply it to your current score. And then, like I mentioned, in the final exam, the current plan is to do 80% alone and 20% is a kind of a collaborative, so from that Thursday, Friday. And so I'll talk more about that in the lectures moving forward, but just in case you're worried about that, that's the current plan of how to utilize that week. All right, so people are starting to head out. So with that, I will end the meeting and wish you best of luck and have a good week and see you all next week. I do have office hours Thursday. I can't answer questions about the midterm, of course, on Thursday. So, but if you have any other questions, general, I have to be careful about content questions because if they come close to the midterm, I don't want to give you any answers. But I do have office hours as usual on Thursday, but feel free to contact me otherwise. And again, have a good week. See you next week.